Okay, well, thank you for inviting me, and good afternoon for you. It's good morning for me with the 6 hour time difference. And now for something totally different. Now, I always enjoy David's talk because he brings me into a realm of mathematics that I wouldn't have gone into myself. But I see the connection, he makes the connection so that towards the end, I get a sense that I want to understand what he was talking about better. And of course, a phone call comes in, but because I'm going to have to suffer through that.
Call from spam.
What I mean is what I'm going to talk about today is I will not try to prove anything, but I will tell you a story about nearly 4th-century-old concept of synchronization and how it manifests itself in living networks. Now, to do that, I have to introduce crucial events, which David was nice enough to introduce in his talk, which are renewal events with a waiting time probability density function that's an inverse power law. So it has a PDF that says a psi of t to the mu, t to the minus mu, where mu is between 1 and 3, which is the domain that he talked about. So when mu is between 1 and 2, you have a non-ergodic process, and when mu is between 2 and 3, you have an ergodic process. And for those of you that need a refresher, an ergodic process is one for which the time averages and the ensemble averages are equal, and a non-ergodic process is one in which they are not. But mu is the interesting factor here, because I put this table up because everything that I'm going to talk about depends on these indices, these inverse power law indices. And they're interesting because the fractal dimension can be defined as d is equal to 2 minus mu, where mu is given by this waiting time PDF. And so when I talk about complexity, complexity is going to be the same as the fractal dimension of a process. So a process will increase in complexity when mu decreases, and will decrease in complexity when mu increases. I'll also introduce another power law, beta, which is for the power spectral density. And these, I introduce it because I want to show that all the power laws that are discussed will be interrelated. So beta is equal to 3 minus mu. And you may recall from David's talk that mu equals 2 was a special case because that's the borderline between ergodic and non-ergodic processes. When mu is equal to 2, beta is equal to 1, and that's a 1 over f inverse power law. And that's what that was 1 over f noise that was found by Shakti in the early 20th century. But we're not going to talk too much about that. Well, we're interested in our scale variables, x of t, where t goes like t to the delta. And delta is equal to mu minus 1 for the non-ergodic case, and it's equal to 1 over mu minus 1 for the ergodic case. And mu greater than or equal to 3 corresponds to delta equal to half. And so you don't have to remember all of the relationships, but just that the relationships exist, and I will discuss what they mean in the context that I'm going to discuss. And that context is the simultaneous measurement of time series from the brain, heart, and lungs. And I'm going to talk about the data from particular neurofeedback training manifests and a new kind of synchrony. What this means is that if you look at any EEG channel, the typical one is shown there over the brain. It looks like nothing so much as noise, but you know it's filled with information. But it's very erratic looking signal. Then you look at the heart, and the heart has this quasi-periodic behavior. A period, when you look at it, it looks like a bimodal oscillator. And then you look at the output of the lungs, and that looks like nothing. If you have any geophysical training, you see it's nothing more than a nonlinear water wave. And you say that these three time series are strongly interacting all the time, and the way in which they interact determines whether we're healthy or we have some kind of malady. And what we're going to demonstrate here by processing experimental data is that these 3 time series manifest a kind of synchrony. And it's not in the time. If you look at the time series, you couldn't see 3 more different looking time series. So we have to look at things other than the amplitude time series and get the unexpected behaviors in the scaling of the time series. And so recalling that the scaling indices are measures of complexity, since mu, the inverse power law for the time interval between crucial events, determines a fractal dimension, which in fact determines the complexity of the underlying process. What we show is that all 3 are crucial event time series. That for the brain, the heart, and the lungs. And we use that information to make some rather remarkable, draw some rather remarkable conclusions. So this is the story of the how we process the data. We take the 3 time series that showed roughly on the in the cartoon on the preceding slide, and the 3 time series here are 10 seconds of actual data that were simultaneously measured. So the black curve is the EEG, the red curve is the respiration, heart rate, or breathing rate, and the blue curve is the heart rate, the electrocardiogram data. So what we want to do is we want to show you that these 3 very different looking time series, can be transformed into the display on the right, which is the entropy for each of the 3 time series versus the log of the time, and the slope of that curve gives a constant slope, and that number is the scaling index for that data set. So you see that for these 3 data sets, in terms of the mu from the power law, inverse power law for the spacing between the crucial events, that the slope for the black curve, which is the EEG data, is more complex because the slope is shallower. Remember, the fractal dimensions, these are 2 minus mu. So you get a value of mu for the black curve, which is less than the value of mu for the red curve, which is less than the value of mu for the blue curve, and the complexity is the inverse of that. So that the black curve has a higher complexity than the breathing data, and the breathing data is higher complexity than the cardiac data. But that's just 10 seconds of data. So what happens when you, first of all, how do you get from the visual impression that you get from the time series data to the processing that you get where you get these straight lines to get the power law index? Well, this is how you do it. We're going to use the heart rate data as an exemplar. That zeta of t, that's the blue curve in the right hand 6 panels. And to show what's being done is that the last period is blown up so that you see that what you do is you take and you draw parallel lines to the x-axis, and every time the curve crosses one of these parallel lines, you call that an event. So that's an event, that's an event, that's an event, that's an event. And you see what happens when you have a feature that's spread out. The time interval is longer between what we're calling events, and when you have a feature that's sharp and close in space, you have a clustering of events. So here you have a large number of events. Here you have very few events. And what this does is this transforms this trace that's physical in space into a time series that if you take the total time interval of interest and you divide by that, so you put it on the unit interval, so that this is now 0 to 1, and every time this newly normalized time series, you cross one of these parallel bars and call that an event, you get this would be a very shallow feature in the trace. This would be a very deep feature in this trace, and it doesn't matter whether you're positive or negative in the trace for the empirical data. For each of the events, whether it's a positive or a negative, we put one unit, just a unit on the diffusion process. So we're going to introduce a diffusion process. The x dt is equal to zeta of t, or x of t is the integral of zeta of t, and it's just given by these localized events that you see, how this is created now. And then this is a diffusion. This is one exemplar of a integration of the discrete data set is this diffusion trajectory. And this is an ensemble of trajectories, all of which start at a given event at 0. Well, that's their since they initiate each of the trajectories at an event, you can pull all the events together and start from 0. And this becomes an ensemble distribution. And from that ensemble distribution, you construct a histogram, and from the histogram, you construct a probability density. And if that probability density has the form 1 over x of the data times the probability that it's x over t to the delta, then when you introduce the entropy for the process minus the integral of p log p, you see that you put in this value for p log p, and what you'll find, this multiplicative coefficient in that logarithm will come on delta log n times f of q dq, which is just the just the first moment of the variable. And you can show that identically you get that for the entropy calculation that the shift from a reference state is equal to delta log n. And that's where if each of these curves satisfies the scaling probability density here of this form, then the change in entropy is delta log n, and that's what you find here. And that's an empirical result. That's due to the processing. So that we don't assume that anything about the data. We demonstrate by means of this processing technique that you get these the values of delta in these extended intervals. So that was for 10 seconds worth of data. Now let's go to 15 minutes worth of data. You get something that looks remarkably different, because what we did there, what we did in the previous slide, we looked at something that filled a region that's about this big. And now we're taking a window of time and moving it down the time series, the empirical time series, and we're calculating the change in the entropy in that time series. And what you find is that that delta, which was a measure of the fractal dimension, remember, delta is equal to, well, let's go back to that slide. Delta is equal to mu minus 1, if mu is between 1 and 2, and mu is equal to 1 plus 1 over delta for mu is equal between 2 and 3. So that when you have when you calculate delta, you're also calculating mu, and so you transform to mu, and then from mu you calculate the fractal dimension. So this is the scaling index delta. Oh, this is wrong. This should be mu of t. Sorry. The point of this is that you take these 66 curves, that's 64 EEG time series. That's the light brown curves here in the background. These are all for the 64 data sets that have been measured in this experiment. And then the red curve is the respiration rate taken simultaneously during this experiment. And the blue curve is the electrocardiogram taken in this experiment. So that all of these quasi oscillating scaling indices in time are for the same, taken simultaneously. And so you see that you have a way of determining the complexity of the heart rate, the heart time series, the lung time, the breathing time series, and the EEG, and they modulate one another. You could also do a transformation and get a direct measure of the complexity of the time series of those three states and see how they, and that's what we call the complexity synchronization, CS. So the multifractal dimension indicates how information is encoded in organ network time series. That I give you a chance for that to sink in, that what we're talking about is we have for these, say the EEG, take one channel of the EEG, that erratic looking signal, fractal dimension, and that's the coded information from that organ network. This dimensional encoding facilitates efficient communication across multiple interacting organ networks. That's something that we've proved in the book Crucial Events, that when you have crucial events in two networks, not necessarily organ networks, but just two networks interacting, the information flows from the more complex system to the less complex system. And that's shown to happen experimentally in the laboratory by people at Delegaire in France, in which you take an aged person or an elderly person who has Parkinson's disease, or just as something is wrong with the gait, and that can be shown for aged people or people with certain kinds of neurodegenerative diseases like Parkinson's. And if you take that elderly person and you have them walk with a young, healthy individual for an hour a day for a few weeks, what you find is gradually the elderly person's gait approaches that of the younger person. And so the gait complexity increases as they walk arm in arm with the younger person. And that experiment has been reproduced by a number of other investigators but the lead investigators is the Delegare group in France. And so the transfer of information is optimal across the organ network interfaces, and that's been proven, shown mathematically. And so the summary of the significance of this result are: the complex synchronization quantifies the most efficient transfer of information between organ networks. Complexity synchronization is a self-organizing phenomenon emerging from the dynamics of these organ networks, the internal dynamics of these organ networks, and it facilitates the transfer of information between the organ systems. And complexity synchronization has been successfully used in person-to-person interactions, arm-in-arm walking, to facilitate rehabilitation. That's another thing about rehabilitation. Say you have a person that undergoes an operation having to do with a lung injury, or they have some respiratory disease, and after they come out, they go into they're put on a mechanical ventilator, which is primarily has a periodic oscillation and ventilation. About 25 years ago, a colleague of mine, Alan Much, who's an MD, decided that the better way to do that is to have the mechanical ventilator have a fractal spectrum of oscillations rather than just being periodic. And he showed with experiments on pigs and later on experiments on humans, not experiments, but yeah, they were experiments. That he had a group of people that came out of, that were in post-op, that were on these biologically variable ventilators, and a group that were on these mechanical ventilators. And the group in the biologically variable ventilators performed markedly better in their terms of the oxygenation of the blood and other indicators of how rapidly they were getting back to the normal breathing cycle. Now, complexities, that's this complexity synchronization has been mimicked between humans and machines to facilitate rehabilitation. And then that's the example I just gave. And there's also the same kind of thing occurs with heart rates. When you have certain kinds of heart rate pathologies, you can hook I'm not the medical person, so I can never remember the medical terminology, which is one of the reasons I didn't go into biology and medicine. You have the same thing with heart rate, that forget about it. Hypothesis. This is what I want to end with. This hypothesis: a compromised biomedical organ network can be rehabilitated to a healthy level of functionality using a protocol for its being systematically driven by a second real or simulated organ network having dynamic fractal properties of a healthy first network, so that these the fractal dimension of a time series, when it's generated by an organ network, is a measure of its health, and the matching between them is the most important feature of how people retain their health or become rehabilitated after they have an injury or a disease. Thank you very much, and I'll take some questions.